Swayam Prabha. Digital India. Educated India.
Okay, so now we are at a very important position in our study of radiation heat transfer, where we will actually do the enclosure analysis. So far last 2 months we have developed the background required to do the radiation analysis. Now we are ready to do the radiation analysis, that is, if there is a n surface enclosure, how do we find the net radiation heat transfer between the various surfaces. Okay. There are several ways of doing it. Undergraduate texts, in undergraduate texts and in undergraduate heat transfer courses, people must have taught you what is known as a network analysis. They will draw radiation resistance, and they will put a series and parallel combination, and they will have an analogy to electrical resistance and solve the problem. But the problem with this network business is, as the number of surfaces increases, it becomes increasingly messy to handle all these resistances. So in this course I will not teach you the network method at all. I will teach you what is called the radiosity radiation method, which is valid from one surface to any number of surfaces. Okay. So what we are going to do essentially is the radiosity please remember that the credit goes to Professor University of Minnesota at Minneapolis. Okay. It used to be the mecca of heat transfer. Once upon a time it used to be the mecca of heat transfer. All legendary names like Eckert, Sparrow, Goldstein, Ebel, T.W. Simon, all those people were there in this lab. Even today Sparrow is there. Of course Professor Eckert died. Sparrow was also the editor of the ASME Journal of Heat Transfer for a long time. Okay. So this was developed in the 60s. We have not got a method which is more powerful than this, so it is eminently programmable on the computer, therefore, and it blends itself easily with CFD calculations. So combined heat transfer problems, radiosity radiation method is very good. Before that we will have to define certain terms before getting into the, this chalk piece is not very good. Okay. Now, so there is a irradiation Gi falling on a surface. This surface has got a emissivity. This is what emissivity is this now? Be more specific. Hemispherical total. It is a hemispherical total emissivity. This is the temperature of the plate. Now out of this Gi, certain portion is reflected, that is rho I Gi. Because this fellow is at a temperature greater than 0 Kelvin, he will also emit. Okay. Okay. Out of the incoming radiation Gi, certain portion is reflected, certain will be absorbed. Alpha I Gi and epsilon I sigma Ti to the power of 4. Now radiosity is the leaving flux, okay, or the leaving radiation. This is equal to okay. The incoming radiation is called G. I am putting Gi because I can be any surface. For a single surface, this subscript is meaningless, but if there are 3, 4 surfaces, Gi refers to I can be 1, 2, 3, 4, it can be G1, G2, G3, G4. So G is also in meters per watts per meter square. Now net radiation we call it as Qi. Okay. For an opaque surface, is this color not very good? Okay, not good, white they have changed the chalk, its friction is more. Okay, let us see. Okay, for an opaque surface, tau 0. Correct, the transmissivity is 0, therefore alpha plus rho plus, this is the fate of the incident radiation. The incident radiation could be absorbed, it could be reflected, or it could be transmitted. For an opaque surface there is no transmission, it is only absorption or reflection. Therefore so substituting in 1, okay, that is the radiosity relation for the ith surface of the enclosure. If it is only one surface, keep it as J or J1, whatever. Now for gray diffuse surface, alpha I equal to, for a gray diffuse surface alpha I equal to epsilon I, correct. Therefore so if you want to calculate the radius, if you want to calculate the radiosity from a particular surface, you need to know the emissivity, you need to know the temperature, and you need to know the irradiation falling on that surface. Okay, if the irradiation is because of radiation from several surfaces, then we have to worry about the radiosity of these several surfaces. That is what the enclosure analysis is all about. But we are now in the preliminary stage, we are trying to first get the expression for net radiation heat transfer, so that we are able to use when we eventually use the enclosure analysis. Now Qi, So, if you are able to find just the irradiation on all the surfaces, you have solved the problem. But it is not so easy to calculate the irradiation on any surface, because the irradiation of any surface is because of the radiosity of other surfaces. So, you should so therefore, we must simultaneously solve either for the radiosities or for the irradiation. We are now trying to develop relationships or expressions for this. We are trying to develop expressions for this net radiative heat transfer. Now, can we have some other relation? Can we have some other expression? Okay, so okay. Gi is correct. I got an expression for Gi, I can substitute for Gi in 10, correct. Simplify, cross multiply and simplify further. Is clear? I am not doing any great stuff, I am just doing some algebraic manipulations, that is all. Now I can cancel Ji. So, what is the difference between, let us call this equation 12. What is the difference between 9 and 12? 9, both are expressions for the heat flux, but 9 is in terms of irradiations, 12 is in terms of radiosities, but our original expression is in terms of both radiosity and irradiation. If you are evaluating the radiosity and irradiation for thousands of elements, if your calculation involves hundreds of thousands or millions of nodes, there is no point in simultaneously storing radiosity and irradiation, because one information on radiosity can be obtained from irradiation or vice versa. Therefore, it makes sense to store only one of the two quantities. So, some people just use the irradiation method where they will just solve for G. Some people use the radiosity method where they will just solve for J. Radiosity irradiation is the general method, but if you have too many nodes, too many calculations to be done, there is no point in storing both J and G. One word of caution, can equation 12 be applied for all cases? It cannot be applied for a black body because there is a singularity, because the denominator becomes 0, okay, not applicable. So, to say that 12 is not applicable for a black body, but in a program if you want to, I have used it in my when I did PhD and I wrote programs for all this radiosity irradiation, I still use this, but I will make black body 0.995 or 999 something, it will still work. If you make 1.00 only, this fellow will go mad, okay, right. So not applicable for so now before starting the radiosity irradiation method, now I gave you expressions for the heat flux. Now what remains is basically to determine the radiosities in an end surface enclosure. But if before doing that, we will do one last thing. Is this clear up to this stage? We have to look at what is called a re-radiating surface. From the name, what do you think a re-radiating surface means? A re-radiating surface is the radiation equivalent of an insulator. In an insulator, the Q equal to 0. That Q could be Q conduction or Q convection, correct? If Q radiation equal to 0 in a radiation problem, then it is called a re-radiating surface. We do not say adiabatic surface, okay. A re-radiating surface is 1. Is the equivalent of the insulated surface in conduction convection. How do we get that re-radiating surface? You can have a surface and back side you make heavy insulation such that no radiation passes through, I mean no heat, there is no conduction or conduction heat transfer, and you prevent all possible opportunities for heat transfer to take place. Then when you do that, whatever is impinging on it must go out, okay. So Ji minus Gi equal to 0, Ji equal to therefore Ji equal to for a re-radiating surface, Ji equal to sigma T to the power of 4. It is a remarkable result, because the radiosity of a re-radiating surface is independent of emissivity. Very significant result. The radiosity of a re-radiating surface is independent of the emissivity, and it will come to an equilibrium temperature of Ti depending upon whatever irradiation it receives from the neighboring fellows. So it will come to some equilibrium temperature. This sigma Ti to the power of 4 is also equal to Gi, okay. So his temperature, whose temperature? The re-radiating surface temperature is decided by his neighbors or by his friends. The other surfaces of the enclosure will decide his temperature, okay. So if there is a 3 surface enclosure, one is the hot surface, for example heat treatment furnace. In surface 1 you are supplying the heat, in surface 3 you are putting some metal objects and heat treating them, and this is the intermediate surface. He is the mediator, he takes the heat from the hot surface and passes it on to the other surfaces. He will come to a temperature which is in between these two, okay. So such re-radiating surfaces are frequently used in furnaces and enclosures, in combustion chambers and so on. Fine. Now let us go to the enclosure analysis. So consider an end surface enclosure. Each of these surfaces okay, each of these surfaces is characterized by hemispherical spectral emissivity and temperature. All of these are grey diffuse opaque surfaces. So what is the total radiation? What is the total radiation which is leaving the surface I, the ith surface of an enclosure? What is the total radiation which is leaving, total radiation leaving the ith surface of an enclosure? Huh? Total Ji is still the flux.
Ji into area.
Ji into Ai, okay. Total radiation leaving an ith surface this must be equal to first part emitted plus reflected. What is the first part? Epsilon I Ai sigma Ti to the power of, yeah. What is that question mark? Not incident, is a reflected part. The reflected part will be rho times of whatever is incident, okay. So we can say that this is correct. We can work on this further. What is this incident coming from other surfaces? This is the question we have to answer. Sum of radiosities into view factors. Good enough? Fair enough? Multiplied by the multiplied by the respective area, because I put watts per meter square into, okay. So I will say incident could be, let us start with A2 if there is a self view factor, it could be correct. So can we write it in a very compact form? Sigma Aj F No, for the ith surface. Very good. J summation j equal to 1 to n. Very good. Is that clear to everybody? Okay. Therefore, but what is AJ What is AJ AIFIJ. Okay. So 1, 2, okay. Can I cut the AI throughout? Therefore, the radiosity of the ith surface Ji equal to epsilon sigma t to the power of 4 plus 1 minus epsilon sigma Fij Jj. Okay, sigma Fij Jj. Do should not get confused. Don't put Fji there. J equal to epsilon sigma t to the power of 4 plus 1 minus epsilon sigma Fij Jj. That Fij can include Fii. If you will be in trouble if you have a concave surface. Otherwise, the first term F11 for the first surface, the second term F22 for the second surface, the third term F33 for the third surface will all be knocked out if you have plane or convex surface. Suppose I give you sphere within a sphere, cylinder within a sphere and cylinder within a cylinder, then some F22 may be non-zero, then you have to consider this. Okay. Once you have this, but what is the what was our nomenclature for this incident radiation? What did we call this incident radiation as? Gi. Therefore, okay, so this is this term is nothing but, therefore if you want to solve for the radiosity in n surface enclosure, the first part is the emission part. Therefore, you must know that the Stefan-Boltzmann's law is at work. So it is just not sigma t to the power of 4, it is epsilon sigma t to the power of 4. So you need to know the hemispherical spectral emissivity. Now you need to know, exploit the Kirchhoff's law and first figure out that it is an opaque surface. Then for a great diffuse surface, rho can be written as 1 minus alpha, and then 1 minus alpha can be written as 1 minus epsilon. So your knowledge of radiative properties comes into effect there, and then when you write sigma Fij Jj, your knowledge of U factors comes into picture. So all that you have studied is incorporated in one single equation, J equal to epsilon sigma T to the power of 4 plus 1 minus epsilon F sigma Fij Jj. In an n surface enclosure, there are n such radiosity relations. If you have n equations in n unknowns, they can be easily solved. You can get all the radiosities. Once you get all the radiosities, you can straight away use the formula for the net radiation heat transfer from any surface in terms of radiosity. Otherwise, if it is only 3 surfaces, if you have the time and the patience, you can individually evaluate the G1, G2, G3 for all the surfaces from the J which you have obtained by simultaneously solving. Then get J minus G for 1, 2, 3 surfaces. Then essentially you solve the problem of radiation heat transfer in an enclosure where there is no conduction and convection. If conduction and convection are there, you will write the additional energy equations and solve, but this will be the radiation portion of the solver. However, here the enclosure is evacuated or is filled with a medium which is not participating in the radiation. Okay, this is the enclosure theory developed by Professor Sparrow and his colleagues at the University of Minnesota, Twin Cities or Minneapolis. Okay, now up to 3 surfaces or max 4 surfaces, we can solve these using hand calculations. If the number of surfaces in the enclosure exceeds 4, you have to use the computer, and since it is a system of simultaneous equations, it is eminently solvable with the iterative Gauss-Seidel method. You do not have to invert, so you can use the Gauss-Seidel method. So you start with some assumption J1 equal to J3 equal to J4 equal to 1000 watts per meter square. Start with that and iterate, then once it converges, then you get all the J's, you get all the G's, and you get the net radiation heat transfer. This is how the enclosure analysis is used. Now let us have a warming up exercise by considering just the net radiation heat transfer from simple one plate. There is only one surface, there is no enclosure, but there is no problem. We know that even though the second surface is not there, we can always close it by hemispherical basket. Shall we do that and see whether the enclosure theory works? Okay, and we will get our familiar relation Q equal to epsilon sigma T to the power of 4 minus T infinity to the power of 4. Let us consider a one surface enclosure. So this is basically the enclosure theory. Is it clear? If you want, you can, we do not call it 31, no problem. We will call it as an example, not a, let us say it is epsilon 1 and T1, outside is T infinity, the outside is considered to be perfectly, it is a perfect emitter, right, 0 reflectivity surroundings, okay. So how many surfaces are there? 2 surface enclosure. There is no need to determine all these view factors. What is F11? 0. F12 is 1. We can stay like this because I will tell you why it is enough to stay like this. J1 this is 1, that gets knocked off, right. because the emissivity of the surroundings is considered to be 1. So it is a waste of time to get f21, f22 and all that. Whenever you have surroundings like this, do not waste time in calculating those view factors. Okay. Now therefore J2 is straight away J1 correct, f11 is 0. Now substituting for J2, okay. What is G1? What is irradiation on 1? What is F11? 0. F12? 1. J2 is sigma T infinity power. What is Q1? J1 minus G1. Right. So we have used the radiosity irradiation method it can be used even for the simplest of problems. This is a formula which you learn probably in high school, or maybe maybe you learnt it again, in the 3rd year heat transfer course. This is one of the most abused formulae in heat transfer. Now having gone through this course, you must know what are the limiting conditions under which this is valid. Single plate at a uniform temperature, the plate is having a uniform radiosity, it is characterized by one hemispherical spectral emissivity, the surroundings temperature is constant, the temperature of the surroundings does not change, there is no irradiation from any other object, there is no other object in the vicinity. Under these conditions, it is a net radiation heat transfer from that body. Simply we cannot use surfaces that will lead to some other, that story will be different. So when you look at that formula, you must see what are the limitations under which that formula can be used, what are the situations under which this formula cannot be used. This must become clear to you. Emissivity 1 it will work, what is the problem? Emissivity 1 it will work, sigma T to the power 4 minus T infinity to the power 4. Which emissivity is 1? Surrounding emissivity is 1, that is okay, because that is because we are treating it as an enclosure. Okay. Now let us go to a equally, so is this fine? Okay. Consider two parallel plates, okay, they are infinitely deep in the, they are also infinite in extent in the direction perpendicular to the plane of the board, okay. Now epsilon 1 T1, this is vacuum. This will happen in insulation. For example, a double pane gas, you can glass, which you see in your air conditioned coach of Rajdhani, Shatabdi Express and all that, there are 2 glass sheets. Probably you can model it using this, okay, or you want to model insulation. There are several layers of insulation, there is an air gap in between and you feel that the thickness is so small that natural convection will not set in, then you can use this. So it need not be completely evacuated. This is surface 1. This infinite in extent is basically to help you figure out that F12 is equal to 1, F12 equal to 1, F11 equal to 0. Now the story is very simple, find out the net radiation heat transfer between the 2 surfaces using enclosure theory. The question is determine Q1 to 2 using enclosure theory. So first write out the radiosity relations for these two. In the radiosity relation you will have view factors. The view factors are so obvious in this geometry. In other geometries, first step is to get the view factors. First step is to get the view factors, second step is to write the radiosity relation, third is to manipulate the radiosity relation and get the radiosities, and the fourth step would be to get Q equal to J minus G, okay. Correct? All of you look at the board, first step, it is so simple, everybody knows this. Now write the radiosity relation. Can I write like this? Fine. I have already incorporated the information I have on the view factors. So it is just mathematical manipulation, that is all. Is it correct? Yeah, good. So okay. So what is the beauty of that expression 4? The beauty of the expression 4 is by inspection I can write an expression for J2. J2 will also be epsilon 1 sigma T1 to the power of 4 plus epsilon 2 sigma T to the power of 4 minus epsilon 1 epsilon 2 sigma T1 to the power of 4, denominator will be the same, okay, by inspection. If people do not believe me, please go through the algebra and get the same result, okay, by inspection. Okay. What is Q1 after all? J1 minus G1, very good. But what is G1 itself? F11 is 0, F11 is 1, therefore G1 equal to J2. Therefore, if you just get J1 minus J2, you have got Q, okay. Is it fine, Ketan? Okay, this is called the parallel plate formula, a very powerful result in radiation. So, sigma T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. If epsilon 1 equal to epsilon 2, the denominator will be 2 by epsilon minus 1. The most important thing, if eventually you want to become researchers, is to always look at what is called as the asymptotic correctness of the result. What I mean by the asymptotic correctness of the result is, when I apply to an extreme case, does it work? I will show you in a minute how to check for the asymptotic correctness of this expression. If the surface 2 is surroundings at T infinity, if the surface 2 is at surroundings at T infinity, what is epsilon 2? 1. 1 by epsilon 2 is 1, that 1 by epsilon 2 minus 1 will get cancelled, T2 will be T infinity, therefore Q will be epsilon sigma T to the power of 4 minus T infinity to the power of 4. Therefore, in the asymptotic limit of the second surface being the ambient at T infinity, this formula works. So, each and every time whenever your approach to any subject, or your approach to any subject should be like that. When you are deriving some results, time and again you have to see whether the asymptotic correctness, whether it makes sense. This can be worked out with paper and pencil. Before going to the computer, you must check all this, fine. So, in tomorrow's class we will take up some interesting examples. Suppose I put a shield in between these two in order to reduce the heat transfer rate, whether the radiation heat transfer will reduce, what will be the equilibrium temperature of that shield. I do not settle down with one shield, I put 2 shields, 3 shields, 4 shields, what will be the heat transfer rate, how do we get the equilibrium temperature under those conditions. We will solve some problems and then go to regular enclosure problems where I give you numerical values and we will work out, fine. So.